Let's do a quick practice problem using the fundamental theorem of calculus part 2. So let's do the integral of x squared from 2 to 5. I've drawn it here like we should always do when we've got a new integration problem to do. What's our next step after drawing it? Well, you might think let's do antiderivatives. We just learned about those. But I say let's put up some guardrails first. Let's do the lower bound, upper bound, and guess procedure that we talked about before. So what's a quick lower bound? So we want the area under this curve. Are we pretty sure that that area is going to be bigger than 0? Yep, pretty sure. What's a better lower bound? Well, I could draw a box whose height is the smallest the function ever gets in that interval. So that would be a box of height 4 and width 5 minus 2. So altogether that's what? 4 times 3 is 12. What can we do for an upper bound? We've been doing upper bounds in blue. It would be a box of height 25. So it would be height of 25 times width of 5 minus 2, which gives you 75. And then our guess would be halfway between those. So 12 plus 75 over 2. And we can think of that as splitting the difference between the height of the upper bound and the height of the lower bound. So based on that drawing, hoping it's a good drawing, do you think the guess will be higher than the true value of the integral or lower than the true value of the integral? So think about that. We'll come back to that later. So now that we have kind of some guardrails and kind of a guess, let's actually do the problem. So we're saying f of x equals x squared. The fundamental theorem says we'll need an antiderivative. What's an antiderivative of x squared? 1/3 x cubed. Now we could do plus a constant, but I'm going to leave it out, and we'll see why later. So we're going to leave out the plus c. You don't have to, but it's just wiser to. So we'll see why later. Well, I guess we'll say it's okay to leave out the plus c. All right, so this integral from 2 to 5 is f of 5, big F of 5 minus big F of 2. That's what the fundamental theorem of calculus part 2 says. What is big F of 5? It's 1/3 times 5 cubed minus 1/3 times 2 cubed. If you do all those fractions, you get 117 over 3, which is 40-ish. Does that work with our lower bound? Yes, it does. Does that work with our upper bound of 75? Yes, it does. Does it work with our guess? Well, what was our guess? Halfway between 12 and 75. It's about 40-ish. Yeah, it's not bad. So it's reasonably close to our guess. Not exactly on, but that's okay. So now that we know the fundamental theorem of calculus part 2, when we're doing formula-based problems, we usually don't want to break them up into little boxes anymore unless the problem explicitly says to. So let's write that down. So now that we know fundamental theorem of calculus part 2, we don't usually break formula-based problems into individual boxes and add those up because that's an approximation. I like approximations, but this is an exact answer. So we don't usually break formula-based integrals into narrow boxes unless told to. Because the FTC part 2 gives us exact answers, those boxes are actually more work and give us a not as exact answer. And let's switch to Desmos to see what just happened. All right, I've got x squared. I've got starting at 2 going to 5. I've got steps of 0.1. I know we just said we wouldn't do small steps anymore. We'd just do antiderivatives, but I wanted to show what it is. And Desmos is graphing a capital F, the cumulative area so far. So if I start back here, big F starts out 0 at A, and then we're adding boxes of small height, and so our big F isn't increasing very quickly, but it is increasing. And as we get farther and farther over, the boxes are taller and taller, so big F is increasing more and more. And we'll bring this up to 5. So then we could say our total area under the curve is big F of B minus big F of A. And big F of A is 0 here because it was the running area under the curve starting at A. But this isn't what we had just said about antiderivatives. Let's go add something. I can't call it big F anymore. We can say big F by hand of x was 1/3 x cubed. And that does not look the same. That's the blue curve. It does not look the same as the purple curve. And it's not going through 0 right there. So that's interesting. Let's try the fundamental theorem of calculus anyway. So I'll say f by hand of b, that's 5, minus f by hand of a. We got 39. We had said before it was basically 40-ish, so that's good enough. We could see what was big F of A. It was 2.66. So y is so the answer we're getting here is 37.95. We could use smaller steps. And now we're getting 38.89. If I use even smaller steps, I get 38.98, so it's sneaking up on 39. But why is this cumulative area so far starting at A not the same curve as our by hand antiderivative there? Well, they are basically the same curve except just shifted up or down. And I know it looks like they're getting closer here, but this vertical distance is the same as that vertical distance. So as long as big F is some antiderivative, it doesn't have to be the antiderivative whose value at A is 0. So we don't have to worry about adding plus c to make the answer at A just 0. All right, next we'll talk about some new notation.